Hello and welcome to our video on Tokamak reactors, how to achieve nuclear fusion. We are Group 1. I'm Colin Teo.
I am Ida.
I am Ren Hang.
I'm Yu Qian.
I'm Shi.
And without further ado, let's begin with part 1 of how nuclear fusion actually works.
Nuclear fusion is a reaction in which two or more atomic nuclei are combined to form one or more different atomic nuclei and subatomic particles. The mass of an atomic nucleus is less than the sum of the individual masses of the free constituent protons and neutrons, and this is known as mass defect. According to mass energy equivalence, E equals to mc squared, where c is the speed of light. A small mass change will cause huge energy released. Nuclear binding energy is the minimum energy that would be required to disassemble the nucleus of an atom into its component parts. It can be expressed in this equation, E equals to delta mc squared, in which delta m is mass defect. Average binding energy is the ratio of the nuclear binding energy and the number of nuclei. It represents the stability. The greater the average binding energy, the more stable the nucleus. We can find that iron has the highest average binding energy. Thus, for any elements with fewer protons than iron, fusion will result in a mass defect and a resultant release in energy. And for any elements with more protons than iron, fusion will result in a release in energy. The average binding energy of the light nuclei is lower than that of heavier nuclei. So when light nuclei fuse, huge energy will be released. So we often use deuterium and tritium as reactants.
Where can we find an example of nuclear fusion happening in nature? One good example is the sun itself, where we know that the sun produces energy for all life forms on Earth, to sustain all life forms on Earth. But how does it do it? It goes through a process called nuclear fusion, which will happen at the core of the sun where gravity is highest. Therefore, there's enough energy to sustain the nuclear fusion reaction. So, the hydrogen gas atoms that are roaming inside the core of the sun will then be heated up and excited to the point whereby the electrons separate from the proton, leaving behind free roaming electrons at really high speed and free roaming protons at really high speed. Then these free roaming protons will then undergo a nuclear fusion reaction called a proton-proton chain reaction, whereby the proton will then collide with another proton at really high speed and energy, overcoming the mutual repulsion force between them to form deuterium, an isotope of hydrogen. At the meantime, the proton will then transmute into a neutron by giving up a neutrino and a positron. Then the positron will then interact with the free roaming electrons to form, or rather to produce energy in the form of gamma rays. These gamma rays will then eventually escape from the sun in the form of visible light. Next, the deuterium will then collide with another proton to give out gamma ray and helium-3 nucleus. Then the helium-3 nucleus will then collide with another helium-3 nucleus to form a helium-4 nucleus and giving out 2 protons as the byproduct. So as you can see, since the 2 protons are a byproduct of the proton-proton chain reaction, this reaction itself is sustainable and will only run out when there's not enough protons, or rather hydrogen gas fuel. Next, I'll pass my time on to Yu Tian to talk to you about how we can sustain nuclear fusion on Earth.
This great attempt using magnetic confinement instead of gravitational confinement is assisted by the Tokamak reactors. Next, we will show you how the Tokamak reactor works. First, fusion in the tokamak begins with the vacuum system. This vacuum is achieved via exhaust pumps in the cryostat. We can see the picture of the tough shell is just the cryostat. Given the volume of the vacuum chamber, this process will take 24 to 48 hours. This is, however, just the secondary use of the cryostat. Its main purpose will be covered later. So why there must be a vacuum system? The main reason is, first, to eliminate organic molecules and other impurities with the nuclear reaction. Otherwise, they will be broken up in plasma and potentially interfere with the nuclear reaction. Second, creating a low-density environment within the vacuum chamber, which is about 1 million times lower than the density of air. Such a low-density environment will be easier for magnetic confinement of plasma. After the vacuum process, the gaseous fuel is injected into the vacuum chamber of the tokamak. In ITER, which is the world's largest magnetic confinement plasma physics experiment, deuterium and tritium are used to achieve fusion. It is worth noting that while deuterium is a renewable resource being found readily in seawater, however, tritium is a limited resource. ITER estimates supply of available tritium globally is around 20 kilograms. So how can we address the issue of limited fuel? First way, it's possible to mitigate this via tritium breeding, which we will discuss later. Or second way, looking for other replaceable fuels. For example, we can using deuterium and deuterium fusion. It's renewable, but is estimated to produce 68% less energy. So we come up with another way, using deuterium and helium-3 fusion. Helium-3 is potentially renewable, as the Moon may possess deposits of helium-3 from exposure to solar winds. If we are able to mine the Moon for helium-3, deuterium and the helium-3 fusion will likely be the best choice for fusion reactor in the future.
Next, let's talk about the external heating systems. In order to make it possible for the fusion to happen, we must turn the gaseous fuel into plasma state and maintain the state in a controlled way. Thus, we need to heat the plasma or the gaseous fuel to extreme temperature, around 150 million Celsius degree, almost 10 times of the temperature of the core of the sun. There are three ways of heating. The first one is ohmic heating, and my teammate will talk about later. The second one is neutral beam injection, and the third one is ion and electron cyclotron heating. Let's do one by one. The neutron beam heating. The working principle of neutron beam heating is to inject electro-neutral particle with high energy into the plasma. And here is the diagram of this process. The first step is called formation. Formation is to get rid of the particle's electrons. Thus, we can heat it or accelerate it in electric field, and this is the second step. And before we inject it to the plasma, we must neutralize the positive charged particles, and then we can inject it. And next is ion and electron cyclotron heating. The essential is to use electromagnetic radiation to heat ions and electrons by resonance. It's very much like how the microwave oven works. Let's look at the diagram. The blue lines. Each blue line indicates at a particular temperature how much energy can water molecule absorb when heated by a particular wavelength of radiation. And every line has a peak. For example, the 0.1 has a peak here. So we can see that at temperature of 0 Celsius degree, if we heat the water molecule with around 4 or 5 centimeters, it absorbs the most energy. So if we use this method to heat the plasma, we use the radiation which can resonate with iron and electrons. So we can heat them the most effectively, and thus is called iron and electron cyclotron heating. And last, is the diagram. Although we talk about these three methods sequentially, and they are not indeed done sequentially. They are done by the same times. And we see a circle, and here is atomic heating. Atomic heating is to heat them use electric current. And here is our iron and electron cyclotron heating. It's use radio frequency heating. And here we have our neutron beam ejection heating. With the three heating methods working together, we can bring the energy of our gaseous free up to a state that allows the fusion to happen.
Moving on to step 4 with magnetic systems. The magnetic systems used at ITER are made of niobium tin and niobium titanium. These materials are superconductive, which means they exhibit zero electrical resistance when cooled below a certain critical temperature. Niobium tin and niobium titanium have critical temperatures of 18.3 Kelvin and 10 Kelvin respectively. It's worth noting that while superconductors have zero resistance, they cannot carry infinite current. Due to the Meissner effect, superconductors can only carry up to a maximum critical current. Niobium tin and niobium titanium are used because they have high critical currents and are able to produce magnetic fields up to 30 Teslas and 15 Teslas respectively. Now, in ITER, we use these superconducting magnets for magnetic confinement of the plasma fuel. First off, let's set up our parameters. We know from Ampere's law that current in a solenoid generates a magnetic field proportional to the current. We also know from Fleming's left-hand rule that a charged particle moving perpendicular to a magnetic field will experience a magnetic force, called a Lorentz force, perpendicular to its direction of motion and the magnetic field. Since this force is always perpendicular to the motion of the particle, this results in circular motion of the charged particle, effectively confining the particle around the magnetic field line. However, what if the particle has some component of its velocity parallel to the magnetic field? Well, in the Tokamak, we will be heating our plasma to very high temperatures, and so they will move very rapidly in random directions. This will thus result in helical motion, and we will need an infinitely long solenoid to confine our particle. Now, that's not very feasible. The solution is toroidal field coils. If we take our solenoid and bend it into a shape of a donut, called a torus in mathematics, we can effectively have an infinitely long solenoid as the charged particle will undergo helical motion in a circle following the magnetic field lines. Now, we know that the magnetic force acting on the charged particle can be calculated by the formula F equals to QB Vy, where Q is the charge of the particle, B is the magnetic field strength, and Vy is the velocity of the particle perpendicular to the magnetic field. The angular acceleration of the particle can also be calculated by the formula alpha equals to Vy squared over r, where r is the radius of the circular motion. Substituting these into Newton's second law of motion, we get r equals to mvy over qb. Using this equation, we can thus find the optimal parameters for r to be as small as possible for effective confinement of our plasma. Number 1, m should be minimized, hence hydrogen, the lightest element, is used. Number 2, Vy should be minimized. However, high values of Vy are inevitable in the Tokamak reactor as we are heating this plasma to very high temperatures. Number 3, Q should be maximized. However, if we increase the charge of our hydrogen, this will actually increase the electrostatic forces of repulsion between nuclei, and this will make fusion itself harder, which is our end goal here. So our last and only option is to maximize B, the toroidal magnetic field strength. This is why superconducting electromagnets are our only option at ITER, as they will produce the strongest magnetic fields. Now, it's worth noting that earlier we used a circular coil as our demonstration. However, this is not practical in reality. In reality, circular coils will not be stable at the scales that ITER is working with. Since the inner coils of the circular solenoid are closer together than the outer coils, this leads to magnetic tension, which can cause stress on the coils. Instead, D-shaped coils will be used in Tokamak, which relieves this tension. Moving on to poloidal field coils. Toroidal field coils aren't enough to confine the plasma due to instabilities that may arise in the plasma due to quantum effects. The poloidal field coils are designed to contribute to plasma stability and further helps keep plasma away from the chamber walls. The exact mechanisms of the poloidal field coils are quite complicated and frankly beyond the scope of this video, but perhaps if you like and subscribe, we'll be able to do more videos on this subject. Moving on to the central solenoid. The role of the central solenoid is not for the confinement of plasma. Rather, it contributes to the heating of the plasma via ohmic heating. Now, what is ohmic heating? By changing the current in the central solenoid, a strong changing magnetic field can be achieved. This will cause a change in the magnetic flux linkage in the plasma, which we know will induce a current that will oppose this change. This phenomenon is known as the Faraday-Lenz law. Now, scientists at ITER have calculated the exact changes in current in each coil of the central solenoid required to achieve maximum induced current in the plasma. As shown in the graph, a maximum sustained current of 15 megaamperes will be induced in the plasma. Each phase of this ramping up and ramping down of current is called a plasma pulse and lasts for about 1,000 seconds. Ohmic heating is what will supply the remaining energy required to heat the plasma to 150 million Kelvin required for fusion. Alright, and here we are at our fifth and final step, energy extraction. Now that we've heated up our plasma to sufficiently high temperatures, fusion reactions will begin to occur. These fusion reactions will release heat as well as high energy neutrons, both of which will be absorbed by the blanket modules on the walls of the vacuum chamber. These blanket modules, now that they're heated, will be water cooled, and this heat will be transferred away where they can be used to run steam generators and thus generate electricity. And there you have it, guys. We have brought energy from fusion. So let's take it from the top and do a quick summary. Step 1, you have some kind of vacuum chamber. Step 2, you inject your gaseous fuel into this vacuum. Step 3, you take some external heating systems and you turn this gaseous fuel into a plasma so that you can activate your magnetic systems in step 4, where you will have a dual purpose of confining the plasma as well as using ohmic heating to finally take that plasma over the edge, over the 150 million Kelvin mark, where fusion will start to occur. After this fusion, it will begin to heat up this whole vacuum chamber, which you can water cool, and then you can use the heat to run some steam engines, or you can run any engine you want, right? Steam engines are just what's going to be used at ITER, guys. You can use whatever engine you want at home. And then you have extracted energy from fusion. It's that simple, guys. 5-step DIY program for fusion. Like and subscribe. Oh wait, no, of course, I'm forgetting something. We promised you earlier a way to get more fuel. Tritium breeding. Tritium breeding can be used to produce more tritium using fusion. After the deuterium-tritium fusion reaction, a neutron is produced. We know that neutrons can be used with lithium to produce more tritium. In the later stages of ITER, special test blanket modules will be used to test several mock-ups of so-called breeding blankets to explore viable techniques of producing and extracting tritium using lithium. If this is possible, it essentially means that we can have a limitless supply of tritium, which in turn means that we will have a limitless supply of fusion energy. Which is, of course, our conclusion. Nuclear fusion is good. Be sure to like and subscribe for possibly more science videos coming your way. That's all from us from here at Group 1. Thanks for watching.